Hi there, this is a realistic DevOps interview simulation focused on Linux, operating systems, and how processes behave in real production environments. These are the kinds of questions that show up in actual interviews, where the goal isn't to recite commands from memory, but to understand how systems behave when things go wrong. Before listening to each answer, pause the video and answer the question out loud as if you were the candidate in the room. That's how you build real interview confidence. If this format is useful to you and you want more long-form DevOps interview simulations like this, subscribe so you don't miss the next one. Let's start with a warm-up. Tell me about a time a Linux-level issue caused a production problem. A strong answer would sound like this. We had a service that started failing intermittently, even though application logs weren't showing obvious errors. After looking closer at the system, I noticed the process had reached the maximum number of open file descriptors. New connections were failing silently, which explained the intermittent behavior. We stabilized the system by restarting the service and temporarily raising the limit, then followed up by fixing the configuration properly and adding monitoring so we'd catch it earlier next time. Next question. How do you usually approach debugging a Linux system you're not familiar with? A solid response would be, I start by getting context. I want to know what the system is supposed to do, what changed recently, and what users are experiencing. Then I look at the basics: load average, CPU usage, memory, disk, and network. That gives me a baseline. From there, I focus on the specific service that's misbehaving and work my way down rather than jumping straight into random commands. Another one. Tell me about a time you had to troubleshoot under pressure. A good answer might be, during an on-call incident, users were reporting timeouts and errors were climbing quickly. I focused first on limiting the blast radius by scaling down traffic and restarting a worker process that was clearly misbehaving. Once the system was stable, I dug deeper and found a memory leak introduced by a recent change. The key was separating immediate stabilization from deeper investigation. Next question. How do you balance speed and safety when making changes on Linux systems? A strong response would be, I try to make the smallest, most reversible change first. If users are impacted, my priority is restoring service safely, not finding the perfect fix immediately. Once things are stable, I make sure any manual changes are documented and turned into proper configuration or automation, so we're not relying on memory or heroics later. One more warm-up. What's a Linux misconception you've seen cause real problems? A good answer would be, one common misconception is assuming low free memory means the system is in trouble. Linux uses memory aggressively for caching, so low free memory can be normal. I've seen unnecessary restarts and even outages caused by people misinterpreting memory metrics instead of looking at actual performance and swap behavior. Let's move into technical and scenario-based questions. What does load average actually tell you on a Linux system, and how do you use it in practice? A strong answer would be, load average tells you how many processes are running or waiting to run, including those blocked on I/O. I never look at it alone. I compare it to the number of CPU cores and then check CPU usage and I/O wait. If load is high and CPU usage is high, it usually means CPU contention. If load is high but CPU usage is low, that often points to I/O or external dependencies slowing things down. Next scenario, a server shows low CPU usage, but applications are still slow. What do you investigate? A solid response would be, I look beyond CPU and start checking I/O wait, disk latency, and network performance. I also check whether threads are blocked, waiting on external services like databases or APIs. Slowness is often caused by something the CPU is waiting on, not the CPU itself, so I widen the investigation instead of assuming the system is fine. Another question. A process is running, but the application appears completely unresponsive. How do you approach debugging that? A strong answer would be, first, I check the process state to see whether it's actively running, sleeping, or stuck in an uninterruptible state. Then I look at logs, open connections, and system-level indicators to see what it might be waiting on. Sometimes a process is technically alive, but blocked on disk, a network call, or a lock, which requires a different response than simply restarting it. Next scenario. What happens when a Linux system starts running out of memory? A good explanation would be, as memory pressure increases, the system may start swapping pages to disk, which can significantly increase latency. If that's not enough, the kernel may invoke the killer and terminate processes to free memory. That's why I focus on monitoring memory trends and swap behavior over time instead of waiting for the system to hit a breaking point. Another one, swap usage is increasing, but there's still available memory. Is that necessarily a problem? A strong response would be, not always. Linux may swap out inactive pages to make room for cache. I look at how quickly swap is growing and whether application latency is affected. If swap usage is stable and performance is fine, it might be normal behavior. If swap is growing rapidly and performance is degrading, that's a sign of real memory pressure. Next scenario, a Linux server has been running for weeks and gradually becomes slower. How do you investigate? A solid answer would be, I look for things that accumulate over time, like memory leaks, growing log files, disk fragmentation, zombie processes, or degraded I/O performance. I compare current metrics with historical baselines to see what's changed. Long-running systems often don't fail suddenly, they slowly degrade, so trend analysis is important. Another question, what's the difference between a process and a thread, and why does that matter operationally? A strong answer would be, a process has its own memory space, while threads share memory within a process. Operationally, that affects isolation and failure behavior. If a process crashes, it's usually contained. If something goes wrong in a multi-threaded application, it can affect everything running in that shared memory space. It also impacts debugging, performance tuning, and how you think about resource limits. Another question. A service keeps restarting automatically. How do you debug that on a Linux system? A good response would be, I check what's managing the service, whether it's a process supervisor, container runtime, or systemed. I look at exit codes, application logs, and system logs to see why it's restarting. Very often it's due to memory limits, crashes, or failing health checks. Understanding who is restarting the service and why is key before trying to fix anything. Another scenario, you log into a Linux server and see a very high load average, but CPU usage is relatively low. Walk me through how you would reason about what's happening. A strong answer would be, when I see high load with low CPU usage, my first assumption is that processes are blocked rather than actively running. I'd check I/O wait to see if the system is waiting on disk operations. I'd also look at the state of the processes contributing to the load, especially whether they're stuck in uninterruptible sleep. From there, I'd investigate disk latency, file system health, and any network-mounted storage. The key is recognizing that load average includes processes waiting on resources, not just CPU usage. Next scenario. An application intermittently freezes for a few seconds at a time, then recovers. Linux metrics don't show obvious spikes. How do you approach this? A solid response would be, I'd start by correlating application-level latency with system activity at a finer granularity. Short freezes often come from brief pauses like garbage collection, disk syncs, or lock contention. I'd look at kernel logs, scheduler activity, and disk flush behavior. I'd also consider whether the application is waiting on external services. Intermittent issues require looking at patterns over time, not just averages. Another question. How do you decide whether to restart a process or keep debugging it live? A strong answer would be, I base that decision on impact and risk. If users are severely impacted and a restart is likely to restore service quickly, I'll restart first to stabilize. If the issue is mild or intermittent, I may keep the process running longer to gather more information. The trade-off is between restoring service fast and preserving state for deeper investigation, and that decision depends on the situation. Next scenario. A Linux server suddenly becomes unreachable over SSH, but monitoring shows it's still running. What are your next steps? A good response would be, I'd first confirm whether this is a network issue or a system issue by checking from multiple locations. If possible, I'd use out-of-band access like a cloud console or management interface. Once I regain access, I'd check system logs, resource usage, and whether SSH processes were starved of CPU or memory. I'd also investigate whether the system hit file descriptor or connection limits that prevented new sessions. Another question: how do context switching and process scheduling affect performance on busy Linux systems? A strong explanation would be: when a system has many runnable processes, the scheduler spends more time switching between them. Excessive context switching increases overhead and reduces useful work. I look at run queue lengths, scheduling delays, and whether workloads are competing unnecessarily. Sometimes the fix isn't more CPU, but better isolation or fewer concurrent processes. Next scenario: a service behaves normally after a restart, but degrades again after several hours. How do you debug this pattern? A solid answer would be: patterns that reset on restart usually point to resource leaks or accumulation issues. I'd track memory usage, open files, threads, and connection counts over time. I'd compare metrics right after restart versus several hours later. That comparison often reveals what's growing and eventually causing degradation. Another question: how do you safely analyze disk performance issues on a production Linux system? A strong response would be: I start with low-impact observation tools to check latency, throughput, and queue depth. I avoid running heavy diagnostics that could make things worse. I look for signs of saturation, slow devices, or contention with background tasks like backups. The goal is to understand whether the disk is overloaded, misconfigured, or simply slower than the workload expects. Next scenario: a process shows as running, but CPU usage is near zero and it's not making progress. What does that tell you? A good answer would be: that usually means the process is waiting on something. It could be blocked on I/O, waiting for a lock, or stuck on a network call. I'd inspect its state, check what resources it's waiting for, and see whether that dependency is healthy. Restarting might fix symptoms, but understanding what it's waiting on prevents recurrence. Another question: how do you think about tuning Linux limits like file descriptors or process counts? A strong explanation would be: I treat limits as guardrails, not arbitrary numbers. I look at how the application behaves under normal and peak load, then set limits that provide headroom without hiding real problems. Raising limits blindly can mask leaks, so I combine tuning with monitoring to make sure usage trends stay healthy. Final question for this section: when troubleshooting Linux issues, how do you decide when the problem is the OS versus the application? A mature answer would be: I look at symptoms across layers. If multiple applications show similar issues at the same time, I suspect the OS or underlying infrastructure. If only one service is affected, it's more likely application-specific. I try to validate assumptions with data rather than blaming one layer too quickly, because misattributing the problem can waste a lot of time. Let's move into the final section of this interview. These questions don't have perfect answers. What I'm listening for here is judgment, prioritization, and how you think when the situation isn't clear. Here's the first scenario. Users are reporting serious slowness across the platform. From a Linux perspective, CPU, memory, disk, and network metrics all look healthy. There are no obvious errors. What do you do next? A strong answer would sound like this: I don't dismiss user reports just because metrics look good. Metrics can lag reality or miss certain failure modes. I'd shift my focus to end-to-end behavior by checking request latency, queue depths, and dependencies outside the host itself. I'd also inspect process states to see if threads are blocked or waiting on something that isn't obvious in high-level metrics. If needed, I'd add temporary logging or tracing to narrow down where requests are stalling. My assumption is that something is wrong until proven otherwise. Next scenario. You SSH into a production Linux server during an incident and notice behavior you don't fully understand. You're under pressure to fix things quickly. How do you proceed? A mature answer would be: I slow myself down mentally, even if the situation is urgent. I gather information first and avoid making changes I can't easily undo. If I don't understand what I'm seeing, I document observations and ask for help rather than guessing. Acting confidently but incorrectly can cause more damage than taking a few extra minutes to understand the system. If action is required, I choose the safest, most reversible option. Another one. Leadership asks you to immediately reboot a Linux server because they believe it will fix the issue. What's your response? A strong response would be, I don't automatically say no, but I don't say yes without evaluating impact. I explain what a reboot will and won't fix, and what the risks are. If a reboot is likely to restore service quickly and the blast radius is understood, I'll coordinate it carefully. If the reboot risks data loss or wider disruption, I propose safer alternatives first. Clear communication matters just as much as the technical decision. Next scenario. You suspect the root cause of an issue is at the kernel or OS level, but you don't have definitive proof. How do you handle that? A thoughtful answer would be, I treat kernel-level suspicion as a hypothesis, not a conclusion. I gather evidence from logs, behavior patterns, and comparisons across systems. If multiple hosts show similar symptoms, that strengthens the case. I involve people with deeper OS expertise early rather than pushing risky changes alone. Kernel-level fixes can have wide impact, so I'm careful to validate assumptions before acting. Final pressure question. During an incident, you make a manual change on a Linux system that resolves the problem. What do you do afterward? A strong answer would be, once the incident is over, I document exactly what I changed and why it worked. Then I focus on turning that manual fix into something repeatable, whether that's configuration management, automation, or a code change. Manual fixes are sometimes necessary, but leaving them undocumented or unautomated creates long-term risk. Closing that loop is part of owning the incident fully. Now take a moment to reflect on this interview. Think about which questions felt straightforward and which ones made you pause or feel uncertain. Those moments usually highlight gaps that matter both in interviews and in real production work. Linux and operating systems aren't about knowing every command. They're about understanding how systems behave under stress and making safe decisions when information is incomplete. Let me know in the comments which question you found the hardest and why. If you want more long-form DevOps interview simulations like this, subscribe so you don't miss the next one.